Very long. That's the way. That's the practice.
Okay. Nathan, can you hear us? Nathan Shammah.
Yes.
Okay, good. Just checking. You'll be up soon, but we got Barish first. So Barish, why don't you start whenever you're ready?
Hi everyone. My name is Barish. I'm a postdoc at Perlmutter. I will talk about pulse level control for Qudit algorithms. This is a work done together with David Eventrelli, and also I will talk about the work in progress with Josh Chubb from Lockheed Martin. So,
And move the mouse. Should work now.
okay. Yeah. So this is the outline of my talk. I first talk about how we control using pulses the bosonic modes. The bosonic modes can be the modes in the cavity, and the goal is to synthesize 1 and 2 Qudit gates, and you want to use them by doing some compilation. We want our approach to be scalable. So, yeah, quant control. So the goal is to trigger transitions between energy levels, and we do this by using resonance frequencies in our drives. There's a drive term D, a complex function. It is an interaction with the cavity mode. A and A dagger are the annihilation and creation operators for a multi-level system. It can be a bosonic mode, and this drive term includes the frequency, resonance frequency. We want to optimize. We want to optimally create this W, which is written in a basis of a certain time-dependent function. We use the references here. They also provide some code. Their code is in GitHub. It's a promising approach for pulse optimization and compilation. So for our Qudit gate synthesis, we use the B-spline basis approach. The details are in the references. So to start with linear oscillator and why it sucks basically, why weight is not useful. Because the frequencies are all the same. So there'll be unwanted transitions to excited levels. The goal is to be able to have distinguishable levels, and we do this by creating some non-linearity. So we have the basic Hamiltonian here, where omega shows the transition between 0 and 1, and the other transitions are also the same, but with some non-linearity, where we can show the Hamiltonian like this. This is not the most general form, but by using the self-cure term, the frequencies will be shifted, and it depends on the energy level K. So we'll be able to distinguish energy levels based on where we are at in this ladder. So if you want to climb from, for example, 0 to n-1, we would need n-1 frequencies, and in the formula that I showed, then you would have a summation over all these W's which are written for each F. So optimization problem gets more and more difficult if you have more and more frequencies. For example, let's look at a scenario where we have a control mode T for transmode. Let's say we use 2 logical levels, and by using a cross-core interaction, we couple it to a Qudit. Let's say it has n levels. So this frequency F is shifted by also this interaction. There is the parenthesis in the end. So yeah, now we have a set of frequencies that we want to use in our pulse optimization, that we should use in our pulse optimization, and they depend on what we occupy in the control mode and also in the Qudit. So, for example, if we have n-1 I mean, if you have n levels from 0 to n minus 1 for Qudit, then the frequency needed, the set of frequencies needed to trigger transitions from k minus 1 to k in this subsystem, in this Qudit one, is the number of frequencies would be m minus 1 times 2. 2 is due to the 2 levels in the control mode, and m minus 1 is due to all the frequencies that you should explore in your Qudit. And there's also for transmon some frequencies needed because we are using 0 and 1, and it's an interaction with the Qudit. There's a whole bunch of frequencies that should be considered in the pulse optimization. So this is for single Qudit, and if it's also useful to write all these frequencies in a one-dimensional manner. I mean, from smaller to the larger, we show here that we have different arrows here. One arrow is, I mean, the dashed arrow is where the cavity changes its number by 1, and the transmon stays the same, or the opposite. Or if you have continuous line here, it corresponds to transmon changes its occupation and cavity stays the same. So this is how resonance frequency work. So you just need to identify the set of frequencies to be able to synthesize your unitary. Things get more involved if you add another oscillator. If you want to synthesize two Qudit gate, for example, then again we have the interaction shift due to interaction, and also due to transmon and Qudit occupations. We can see that the number of frequencies in the transmon becomes n squared, and also there are m minus 1 times 2 frequencies for the for each Qudit, and we have 2 Qudits, so total number of frequencies become n squared plus 2 n minus 1 times 2. So I'm writing this frequency because number of parameters in optimization is proportional to number of frequencies, and it gives a kind of measure for, sorry, switch to, it gives a measure of how difficult optimization will get. And here I show a composite system of 2 Qudits and a control mode. And yeah, if you want to synthesize a unitary which is dense, which uses all these frequencies in your system, then yeah, things get kind of crowded. We check the synthesis approach for a case study, which is for quantum heuristics. It provides useful test cases because lots of parameters are needed to synthesize such gates. We checked a single bosonic mode gate and two Qudit gates. Both of them are parameterized gates used in QAW, for example. Yeah, we took QAW as an example, and we synthesized the gates. We check what resources we need. So our paper is on arXiv. It's based on the numerical gate synthesis, but the goal is bigger. After you synthesize the gates, you want to be able to compile your algorithms into these gates, and these pulses may be useful, but if you, for example, look at if you have Q Qudit gates, then transmon is overcrowded by n to the q frequencies. Probably you will need, probably it will be enough to have 1 Qudit and 2 Qudit gates, but still it depends on the architecture, which is a co-design approach at SHMEM we are creating. So yeah, one and 2 Qudit gates are useful, but still there's the question of what should be the schedule. And there are modes which are watching the 1 and 2 Qudit gates as a spectator. So there'll be some unwanted transitions. Are those under control? So there are several questions that we are currently looking at after dealing with 1 and 2 Qudit gates. would that be useful in a Qudit environment? So that's the general question. So our approach as a summary is we have a gate, we have a circuit which represents an algorithm. It includes the Qudit gates. Since gates are not available like in qubits, we don't have that many freedom. We don't really know where we start with, so we synthesize the gates we need, and we did this in pulse level because we have more control. So if we optimize the pulses, and then the next step is to compilation and run your algorithm in realistic setting. Gates are also synthesized in realistic setting, but if you have more modes, extra noise or other stuff, will your gates still be safe to use in your algorithm? That's a big question. So the punchline is pulse optimization is useful, and we synthesize the gates that can be useful in a near-term SQMS architecture. And we are currently moving beyond the case studies. One important topic is we should do benchmarks depending on the problem type. We need different resources, so we are currently doing some resource estimates depending on number of frequencies or how long a pulse optimization takes. And another thing is the realistic implementation. If there are several modes which may overcrowd the bandwidth of pulses, or if they just sit there and watch the other gates, what is the effect of them, as I said. So, and the spectator mode effect, in other words. So, and also the compilation and schedule, what one can apply sequential gates or parallel gates. What is the optimal way to find it? So I'm asking mostly questions, but we are currently trying to find some answers to these questions. And the last thing is we want to move beyond 0.99, obviously, to have accurate control. And the bigger goal is to be able to use these pulses in a compiler setting. So I didn't give much answer about scalable stuff, but we are organizing a workshop in Chicago this summer. You're all invited. We invited people from all control stack, from algorithms to implementation. We will discuss scaling up of quantum. I hope to share soon a description and invitation with you guys. So, thank you for listening. If you have any questions.
Quick question. Yes.
So what is the computational cost? Usually these optimal first generation is quite a long time.
Yeah, that's right. For two Qudit gates and one Qudit gate which has 8 levels, they are coupled to transmons with 2 logical levels, and we also have guard levels to check the leakage. It's not. It can take in the order of day or so. Also considering all the parameters we need for an algorithm, and after you synthesize the gates, you get a lookup table. But the question is, if your parameter is not in the lookup table, you should find a way, maybe a machine learning method, to find the pulses that are not available in lookup table, some kind of interpolation. So yeah, that's not the full answer. Maybe the gates you synthesize may not be enough, but as I said, it takes on order of day. But in the paper, in the last page in the appendix, there's some answer to your question.
All right, thanks, Barish.
Nathan, the next week.
Nathan's the next speaker.
You should share your screen, Nathan, if you can.
Hi everyone, can you hear me?
We can, yes. Start whenever
Yeah.
you're.
Yeah, so thanks everyone. I'm sorry I cannot be there in person. And it's always this awkward situation of a hybrid format, but I'm grateful to the organizers for inviting me and for allowing me to participate remotely. So yes, I'm gonna speak about quantum error mitigation with an open source project called Mythic that we've been developing at the Unity Fund, where I work full time. And for any information, feel free to send me an email at nathan@unity.fund. I'm part of SQMS ecosystem task force, and I'm also visiting at the University of Milan and at RICAN. So I don't know how many of you know about Unity Fund. I cannot read the room, and my setup does not allow me to see any reaction, but I thought it was, even if it's a lightning talk, to have 2 slides about Unity Fund more in general. So it's a non-profit based in the US that has actually a global team and global reach with a mission to create a quantum technology ecosystem that benefits the most people. So it really started as a lightweight effort with fast grants. I guess everyone in the room can agree that grant writing and bureaucracy can be a headache. And so the nonprofit has awarded now 54 microgrants. They're really like micro grants because they're $4,000 with no strings attached, an application that can be made in 2 minutes online with a video. So the awardees are quite diverse audience coming from 22 countries with various backgrounds. I would say mostly students, but not only researchers, also folks who want to get into quantum, and maybe they're like, full stack software developers. And it happens to be that one of my coworkers that is now technical staff at Unity Fund wrote the fastest quantum simulator called Crack at the time that was actually beating the state of the art. There's also like more traditional academic output out of these efforts, 16 publications so far, and a focus on open source quantum software. So these Python libraries, but also Julia, Scala, other languages, and a vibrant community. And this is more like pre-competitive stage. So the focus is not really into tech transfer for market capture or startups creation, but it sometimes happens that these become either startups with venture backing or non-profit organizations themselves, such as QAW. So today I'm going to speak about Mythic, this Python toolkit for quantum error mitigation. We also launched this week Metric, which is actually a website, metric.info, thought to be a community-driven repository to really find the common benchmarks of the state of the art. So everyone can submit their metric to Metric, and Metric with a Q, of course. And also, it's a great way to aggregate and collect the literature. So yeah, I hope it will be like companion and we'll receive more feedback. Quickly summarizing what Unity Fund does beyond developing Mythic, which is a multi-year effort. We also support established projects. So I myself am a user, contributor, and now I'm an admin of Qudit. And I will spend one slide on a spin-off of, let's say, module of Qudit, which is called Qudit QIP, which has become a package itself for quantum computing, quantum circuit simulation at the noise level. And as you may know, Qtip is very good at simulating noise. So it's also becoming more relevant. It was more on open quantum optics, but it's becoming more relevant in this NISC era. We're also organizing the decentralized remote hackathon called Unitary Hack. You can check it at unitaryhack.dev. There's 25 participating projects, some also from folks involved in the 2 NQIs that are part of this workshop. So, but anyone can sign up or participate in the project. And more activities going on open platform discord.unitary.fun, where we also host open community calls. So actually the Mythic development is in the open weekly on Wednesday and Friday. And also like Penny Lane and other projects such as a Quantum Intermediate Representation Alliance or QTIP hold their calls there. So hoping that I didn't eat all my time with this introduction, I just thought that maybe have one slide on error mitigation and basically like besides the technicalities and details that I'm sure the room knows about error correction and why it is necessary to build a scalable quantum computer, is that although I may be challenged because there are like some research being put out on quantum error correction, but to really have an impact right now, it's unfeasible because of the status of like noise, high level of noise in quantum computers. So error mitigation is actually a set of techniques, actually is a field that is emerging, taking also like solutions that were previously known with other names, starting from dynamical decoupling. But in cases in which basically what the difference with respect to quantum error correction is that you do not need generally intermediate measurements, feedback, and correction operations based on the measured syndrome. So the main idea is to perform multiple and different noisy quantum computations, collect the results, and then infer the ideal expectation values from noisy data. So generally, it's unscalable, but it is at least doable right now on near-term quantum computers. And there is exciting research, I think, going into the direction that maybe one could take the best of the two worlds in this NISC time. So using error mitigation to lower some of the constraints, and of course also like the efficacy of quantum error correction, such as this recent result from IBM. So let me get to Mythic. You can find more information about this software package that we're developing at Unitary Fund with a wide community at mythic.readthedocs.io, which is, Norm was speaking about documentation. I think I'm proud to say that we have a beautiful documentation that it's HTML based, but also with notebooks. But if you print it, it's a whopping, 290 pages, just because we have everything in the API docs out there, but we also have user guides, we have examples, and everything is thoroughly tested, documented, and set up with best practices of open source software development with continuous integration and development. So the scope is really to provide a toolkit to easily apply different error mitigation techniques and to basically make the life of a user as easy as possible, because there is actually proliferation of frameworks and no one wants to learn 20 different languages, and Mythic is a new language itself. So it's actually built on top of Circ, but for the representation of quantum circuits, but it actually can be used also with a starting point with quantum circuits written in Qiskit, Pikewill, Bracket, Penny Lane, and also the OpenQASM standard. And basically, it's designed to be backend independent. I have a slide about that. It collects a series of quite independent techniques that also can be compounded, so they can be integrated with each other. And in this lightning talk, I don't have the time to get into the details, of course, but I wanted to collect at least the names here. Maybe some of you may have heard about dynamical decoupling, which actually comes from the control theory and at the pulse level. what we're doing with all these techniques, since most folks that have access at the gate level to quantum computers, is to rewrite or think of new techniques at the gate level. So zero noise extrapolation is a technique that was initially proposed imagining pulse stretching, and we're implementing it what we call digital zero noise extrapolation, because we insert gates in order to then infer a better result. I mean, it's hard to explain it in a single phrase, but I have a slide about it. Other techniques are probabilistic error cancellation, Clifford data regression, and I mentioned dynamical decoupling, what we call digital dynamical decoupling, which means inserting gates instead of having pulse level control. And you can see a code map on the bottom right. I hope it's big enough. It doesn't yet have dynamical decoupling because we're developing it in these months. So the typical workflow for a user is to start with their language of choice or framework of choice, Qiskit, Circ, you name it. You have a quantum program, you execute it on a backend, which could be a quantum processing unit or a simulator, such as with Qudit or other simulators provided by in these languages. And then people collect expectation values. At least in this NISQ era, most algorithms rely on expectation values. You could also get bit strings, but generally in variational algorithms, one wants the expectation value. So the idea of Mythic is to be actually a quite thin layer in between these two tasks, like sending the program and obtaining the result. And how it works with most techniques, actually, you can formalize it this way. You actually send a bunch of programs that have some characteristic depending on the technique. And then you collect many results and you perform some inference, classical inference to improve on the result that you are trying to estimate. So it's sort of what we call a mix of quantum sampling and classical inference. And this is really like a very, sketch, hand-wavy slide about zero noise extrapolation in case you are not familiar with it. So generally you want to run your algorithm at the zero noise level that you see here for this noise scale factor on the x-axis, but you are limited at running the device or simulator, a noisy simulator, at a level that we can call 1. So the idea behind zero noise extrapolation is that you can actually make your program longer, run for more time, so that the noise level will actually go up artificially, but then actually do more sampling of this landscape, and then be able to extrapolate to the zero noise limit. And it's really, as you can see, it's again these two parts: one in which you launch many programs, and in this case you're extending the noise scale factor, and the other one is in which you're applying some inference method, which in this case is just curve fitting. But there's like different curve fitting you can use. Originally, it has been proposed with Richardson extrapolation, but there are also other classical inference methods. So I guess I'm basically over time. I just wanted to say that Mythic is being used by the community, and we seek feedback and also like research collaboration with other folks. Besides the research we perform at Unitary Fund, we have tested Mythic on Rigetti devices through AWS using what is called verbatim compilation. Actually, this is it's basically controlling the native gate set, something that recently also IonQ has provided and can also be controlled with IBM. Folks have used Mythic to improve basically quantum simulation techniques and models, such as in quantum field theory models. This is in this paper in the center that you see, and also to improve what's been named effective quantum volume, so of devices. Briefly, really briefly, I'll say that we are performing research with partners, and but we're seeking also for more collaborations, also to test the limits and applicability of error mitigation techniques. So the first paper on the left is actually creating a more general framework to think about error mitigation techniques, and extending with noise, like noise extended probabilistic error cancellation, which is a technique that I mentioned before, that can be visualized in a way that is to some extent homogeneous with respect to zero noise extrapolation. And on the right, instead, you can see a paper that is actually just a manuscript on the archive right now under review, validating the robustness and reliability of zero noise extrapolation against correlated noise, benchmarking it with different noise scaling models, not only at the gate level, but also at the pulse level. And you see in the plot on the right, actually different noise spectrums that we studied, from pink noise to low pass filters to white noise. So I don't have any idea of how much I'm over time, so I think I will just wrap up. Right, Norma, is when the chair stands up, I'm over. Someone is over time. I just mentioned that for Qtip QAP, it's this module that allows to simulate also noisy quantum devices, even if you don't have any processor, and it's very useful for studying noise models. And finally, I just wanted to mention this summer school in Florence, organized by SQMS, where there will be some error mitigation lectures and labs that I'm glad to participate to. And please tell, or if you're a student, please look for application and support, because applications have just opened. So thank you very much.
Questions?
Does anybody have like one quick question? We're way over time.
Yeah, I've got a quick question, if I can ask. I'm Peter Ort. So
Yeah, sure.
What's the standard way to get involved with like development of MIDIC? I mean, is there like, in terms of like, you know, what features would be useful to implement, or if there is a student, say, who is interested or implemented a feature, how can we make this kind of part of the official package? What's like the usual way to do that?
Yeah, I can follow up in detail via email, but basically come to a community call on Discord, but also you can find all information on GitHub, there is a roadmap with, you know, the plan, what we want to do for 2022, for example. And then we do the development milestones that are 1 month long. And if people show up or even just comment asynchronously on GitHub, we will assign issues and collaborate with them to try to solve them and port some techniques there.
Thank you.
Yeah, you're welcome.
Okay, can everybody hear me? Okay, so I will try to be quick. My name is Ang Li. I'm a computer scientist from PNL. My background is mainly on the HPC and GPUs. So I'm here to talk about the simulation tool for quantum circuit simulation on the HPC, particularly the GPU-based clusters. And this is work collaborated with Microsoft folks. Okay, so I will basically talk about the umbrella product called NWQSim. We borrowed the name from NWCam, and within the umbrella, we have the state vector simulator called SVSim and the density metric simulator called DMSim. So the NWQSim originated from PNL LDRE projects and later was supported mainly by the QSC project. We are working on the Q#, QR, and XCCC front-end integration. The goal is to have high performance computer backed simulator for the pre-exascale HPC and later for the exascale systems. So here we show the structure of the software. As I mentioned, we have the density metric simulator and the scale vector simulator. For the front end, we have the C++ and the Python APIs that can support the Q#, QR, OpenQASM 2, and Qudit. And the back end, we support the CPUs, GPUs, NVIDIA, AMD GPUs, and also Xeon Phi. The details about the two simulators, the technical details can be found in our supercomputing 20 and 21 papers. So these are the gates that we currently support in the simulator. The left-hand side is mainly the gates that's from the OpenQASM 2 standard, and on the right-hand side are those gates that are defined by the QAW runtime. And then I will talk about this state vector simulator. The SVSim is built upon this shared memory communication model for either like a remote data access. Basically, we over the CPUs or the GPU memory, we kind of share the whole state vector space for the circuit. For the state vector, and then we apply the gates upon like each of the devices. And the nice things for this shared memory communication model is it can provide a very fine-grained communication and computation overlap, and especially for the NV shared memory and ROC shared memory, they provide a way of forming GPU-side communication without any CPU intervention to avoid the high cost of data movement between the CPUs and GPUs. Here we show the structure of the simulator. We perform these tests on the different devices for the single device scale up on CPUs, GPUs, Xeon Phi, and this test was performed on the IBM Power 9 and the NVIDIA V100 GPU-based Summit system on CPUs and GPUs. I just quickly show some of the results. These benchmarks are from the QASM bench. That's is another thrust of our work. And we perform this testing on all these platforms just shown. And the observation is for small circuits, the CPU performs better, while for large circuits with sufficient workloads that can fit the GPUs actually work better. We didn't observe sufficiently enough like a performance boost from the V100 to the A100, but you will see later that on the density metric simulator, we actually observe very good performance gains by this architecture change. And we are working on the performance optimization for the M100 AMD GPUs because currently it shows inferior performance. Here we show the performance scaling out on Summit in terms of CPUs and GPUs from 4 GPUs up to 1024 GPUs. As you can see, like this is kind of strong speed. Here we compare the performance of single device upon like Qudit Air, Circ, QSim, and the Q# simulator, and the observation is that we can have around 10x speed up. This DMSim is an upgraded version of our original DMSim implementation. So this is a very fresh results that I generated these days. Here we show the current work, this system level simulation using the DMSim. Here is the framework. We have we can convert OpenQASM 3, OpenQASM 2, Qudit, Q#. These three are through the QCore tool that developed at Oak Ridge to the QAR representation based like logical circuits, and through some conversion tool developed by our Microsoft folks that we can target the different backend devices with their basis gates. For example, for IBM Q are these device basis gates and Rigetti for these. So we can generate the QR basis circuits for a particular device. And these circuits are fed into the DMSIM. Then we have this, then we input the topology, for example, the IBM Q, the Rigetti INQ, and also we inject the noise models based on the T1, T2 duration, readout error, etc. And then we perform this simulation on the HPC, particularly GPU-based HPCs, including Summit and Perlmutter. We also test on single node of Spark. So we give some testing here. This for these circuits, and we simulate. We target the IBM Q basis gates with these basis gates. And the target platform is Guadalupe with 16 qubits. We inject the depolarization and thermal relaxation noise, and these are performed on testing are performed on the Perlmutter and the Summit. I'll show you some of these results. These are results are generated like 1 or 2 days ago. So for this testing, we use 6 Summit nodes. We use 32 V100 GPUs. This is 16 qubits density matrix simulation with a noise. So either although we show the qubits here, these are the number of qubits in the circuit, but actually we simulate these. Here are the logical gates before the gate fusion, and these are the actual metrics that we simulate internally after the gate fusion. Gate fusion is performed on a single qubit and 2 qubits, but there are some limitation on the density matrix simulation, so we can perform only limited scale of gate fusion. But here shows the time without gate fusion and the time with gate fusion. As you can see, the gate fusion plays a nice job. Here we show the Perlmutter evaluation results. We use 2 Perlmutter nodes, 8 A100 GPUs perform the same kind of simulation. What we can observe is that using only 8 A100 GPUs, we can obtain similar but slightly better performance than using the 32 V100 GPUs on Summit. Some more results on Perlmutter is we test a QPE circuit using 128 nodes with 512 A100 GPUs. We use the maximum hours, but still it didn't finish. It has 15 qubits density matrix simulation with a noise. And what we observe is around 0.75 milliseconds per logical gate or 7.3 milliseconds per internal matrix each operations. And on Summit, this number is kind of double. I still wait for some job to finish on Perlmutter, but this shows the scaling of from like 8 GPUs, 32 GPUs, 128 GPUs, 512 GPUs. Because every time you add 1 more qubits for the density matrix simulation, you basically need 4 times of the resources. Yeah, finally, I want to acknowledge the QSE project. And that's it. Any question?
Questions, if there's any. You can also ask them questions at lunch. That'd be fine.
Yeah.
Jack, let's just do that. And we have one more topic, I think. We have one more topic. Yes, Jason Saroni, are you online?
Yes, hello.
Hello.
Hi.
Yes, share your screen.
Yes, I would like to. Is it showing?
Yes, we can see it.
Okay,
Feel free to start when you're ready.
I'm ready now. Thanks. Hi, everyone. My name is Jason Saroni. Thank you so much for this opportunity to present today. So I'll be presenting on simulating thermal quantum quenches with a variational quantum algorithm. And the motivation of this talk is that running thermal quantum quenches on a noising intermediate scale quantum device will enable us to study interesting physics out of equilibrium. So to do this, we'll do benchmarks on classical devices. And in particular, we develop a hybrid algorithm that measures thermal state preparation using density matrix quantum Monte Carlo with a variational quantum algorithm called adaptive variational quantum dynamics simulation. And we use this to study sudden quenches in the antiferromagnetic mixed field Ising model from a thermal initial state. And finally, I'll give an outlook of what we can do next based on the results that I'll present. So why bring together AVQDS and DMQMC? So AVQDS gives very good agreement with results that you'd expect using unitary exact time evolution for small time scales. And also the circuit depth that we get from AVQDS is much shorter than that one would get from using naive trotter simulations for the same final time by about 2 orders of magnitude, as one can see from the picture on the right. And from the DMQMC side, we can approximate thermal density matrices at system sizes that are beyond exact diagonalization. So this method is attractive to merge together with AVQDS, where we can get quantum advantage while also looking to study bigger system sizes. So to briefly describe how AVQDS works, so how it works is that it's based on an ansatz, that's a guess of the wave function, that's expanded along the time evolution path such that a certain cost function is minimized. So it works at the level of the density matrix, where in this case, we have equations of motion, von Neumann equation of motion, and the cost function is defined as the McLaughlin distance, the Frobenius norm of the difference between the quantities within the double bars. And in expanding this expression, one is able to get so-called M matrix and V vectors that are associated with the evolution of the variational parameters of the ansatz. So the theta mu and A mu are the variational parameters and the corresponding operators that are given by AVQDS. And they're given in such a way that you will always be below a certain threshold of the McLaughlin distance. So on the DMQMC side, we start at infinite temperature, which is beta equals 0. So the density matrix is going to be fully diagonal in this starting point, and then evolve according to an equation of motion such that starting to populate the diagonal entries with so-called type operators that are defined using outer product of the computational Z basis states weighted with an appropriate coefficient. They will either get spawned or they'll move to the right or to the left according to certain probabilities, such that they sample the entire space and ultimately at a finite temperature give a good statistical approximation of the exact density matrix. And so this method is brought together with DMQMC, where we reduce the problem of finding the thermal, in this case, thermal static magnetization, to a pure state problem where one can weight the appropriate density matrix elements of an observable with the density matrix, and we parallelize the preparation of each of the states to high performance quantum high performance cluster. And to find off-diagonal elements, one can simply just use plus and minus superposition states, since it's more convenient to straightforwardly calculate the diagonal entries. And the density matrix in this case for this Hamiltonian is symmetric, and it's also Hermitian. So we'll use that one symmetry to reduce the amount of work that is required to simulate the thermal quantum quench. And I'll notice that in this mixed field Ising model, I have an additional term that's small compared to the others, the HS term. And that's just to pick up one of the Neal states, since the ground state is twofold degenerate. And so in this picture to the right, I have a phase diagram that is made using the Binder cumulant for different temperatures. And to the far left is the antiferromagnetic phase. And we would like to consider different quenches to different locations. So in particular, we'll look at how starting at a different location of the phase diagram influences how much of the density matrix weights are distributed, basically the sparsity of the density matrix, and how much we can truncate by only considering a few density matrix elements that are of the highest weight. So when we increase the value of G naught, we'll see from the Hamiltonian that we go from having a density matrix that's more diagonal to one that has more off-diagonal elements, and that increases. So that means that one density matrix element will have a less weight compared to the others. But you can see that if you account for about 100 of them, in this case, that's still at least an order of magnitude less than the total number. We already have a very good agreement of, compared to the exact result, where rho prime is the density matrix of the truncated density matrix, and rho is the exact. And here, in the case where U naught is 0.1, you see that we already have very good convergence, even with just 5 density matrix elements to the exact. And to the right, for G naught equals 1.0, you can see that you start to have off-diagonal elements, but most of the entries where this is a picture of the density matrix for system size L equals 4 with 16 rows and 16 columns, there are a lot of empty spaces, and that means you don't have to simulate all of these empty spaces, but just take the highest weight. So for L equals 6, when you have an agreement to the exact result, just by going from 10 to 70, you can see that you get a better convergence. And so this means that one can reduce the amount of work that is required to do simulations with thermal states by parallelizing the preparation and then only considering highest weight entries. And in this case, you can see that the final fidelity is very high for all of the elements considered. And finally, you can look at different quenches and change basis of the density matrix, depending on which side of the phase one is. The X basis or the Z basis will give a more sparse density matrix, and thus better convergence from these 4 graphs. Okay, so the summary is that we have a hybrid algorithm that measures thermal state preparation using GMQMC and ABQDS, and we compared results to exact diagonalization. And we can further do more of implementing on a quantum device by calculating M matrix and V vector, and also find global phase dependent quantities like the thermal or Schmidt echo, and extend to calculating correlation functions at finite temperature. Sorry, I couldn't share my video because the internet is not very good, but I'll take any questions. Thanks.
Quick question before lunch, anybody? Looks like everyone's pretty hungry, Jason. So thank you very much. And
Okay,
that's the end of this session.
thank you so much.
We'll be back at 2 o'clock.